Welcome back. In this video, we are going to solve this problem that is taken from chapter number 6, fatigue failure resulting from variable loading, and book name is Design of Machine Element by Shigley, Mechanical Engineering Design. So statement of the problem is a flat leaf spring is used to retain an oscillating flat face follower in contact with a plate came. The follower range of motion is 2 inch and fixed, so the alternating component of force, bending moment, and stress are fixed too. The spring is preloaded to adjust various came speed. The preload must be increased to prevent follower float or jump. For the lower speed, and the preload should be decreased to obtain longer life of came and follower surface. The spring is steel cantilever 32-inch long, 2-inch wide and 1 over 4-inch thick as shown in figure 6-38A. The spring strength are 150, ultimate tensile strength, yield strength is 127 kpsi and endurance limit is 28 kpsi. Endurance strength is 28 kpsi fully corrected. The total came motion is 2 inch. The designer wished to preload the spring by deflecting it 2 inch for low speed and 5 inch for high speed. So you have to identify the stresses, amplitude and mean stress value as per table that is shown. You have to fill that. And in part B, what are the strength factor of safety corresponding to 2 inch and 5 inch in preload based on Gerber-Langer and modified Goodman failure criteria. And at last, plot the Gerber-Langer and modified Goodman failure criteria curve with the load line. So you can see this is the spring, leaf spring, and this is the flat face follower that is connected with this plate came. The plate came can have many shape, but here we have taken a roller, a circular follower, and this is offset at this point. Clear? And the cross section is shown that this leaf spring is 2 inch in width. Clear? And 1 over 4 inch thickness, and the total length is 32 inch. So for a preload of 2 inch that is used for small speed, and for a preload of 5 inch that is taken for high speed, and this follower can move maximum up to 2 inch distance. So let's start with the solution. What will be the first step is that you can see that this spring acts as a cantilever beam, so definitely during follower oscillation motion there will be a force acting on this spring and it acts as a cantilever beam. So definitely at this fixed end we will have a moment, and we will find this moment by using the table that is from table A-9. So let me draw the free body diagram like that. This is the leaf spring that act as a cantilever beam. At this we have force due to the follower, came and follower that is acting on this beam, and this total length is L, which is equal to 32 inch. So definitely the due to this force there will be a bending moment act at the end of this beam, and we will find this bending moment M that will be equal to F multiplied by L, or we can also write force multiplied by this length 32 inch. So this moment will be equal to 32 F, and unit will be pounds into inch. Okay, now we will go to the table from table A-9 beam 1. What we will do is that we will find the force and deflection due to this force, because due to this force this beam will deflect like that. So what we will do is that we will go to table of A-9 beam 1 from appendices. Let's move to the table A-9. So what you have to do is that you have to go to the end of the book useful tables, and then table A-9 beam 1. So you can see this is table A-9. This is table A-9 1. A-9 1. That is cantilever. I will show you. This is A-9, but that is cantilever uniform load. So in our case, we have cantilever and loads is this. Clear? So like it's like that. So you can see that this deflection y can be written as like this, and maximum deflection at the free end will be this one. So we will take this y max is equal to negative sign shows that it is downward, but we are taking this deflection as fl cube over 3ei. So from here you will get this f will be equal to 3ei multiply by this y divided by l cube. Clear? And this will be our force that is producing this deflection. So I will write this over there. So I can write force and deflection y in a cantilever are given by this f is equal to 3ei multiplied by y divided by l cube, where I is second moment of inertia of this beam, E is modulus of elasticity, y is maximum deflection, and L is the length of the beam. Now we know that due to bending moment or due to bending moment, bending stress will be generated in this leaf spring that acts as cantilever beam. And we know that bending stress is equal to sigma, and that is m into c divided by I. Now what will be the moment of inertia? So you can see from the given data, we have been given that the cross section of this leaf spring is that this is 2 inch and this height is 1/4 inch. So this will be its, if you take half of this, so this will be its center. Clear? Now the moment of inertia for I for rectangular cross section can be written as I is equal to 1/12 bh cube. So you can just plug in the value 1/12. B is 2 inch and 1/4 is actually 0.25 power cube. So we will calculate that 0.25 cube multiply by 2 divide by 12 will give you 0.00260. So I is equal to 0.00260 and unit will be inch power 4. Now you have this I. So what you can do is that you can just plug it in this formula. So we know that sigma is equal to m into c divided by I. We can say that here you can see m is 32f. So 32 times f multiplied by c divided by I. And we can write this sigma is 32 multiplied by f is this one, which can be written as 3ei into y divided by L cube and C is there and I is also there. So sigma is equal to this I will cancel each other. So we will get 32 into 3. 32 multiplied by 3 is 96. So 96 E I Y over L cube into C over I. Okay, so this I will cut with this I. So we will get sigma is equal to 96 E Y multiply by C divided by L cube. Okay, now what we will do is that let this term 96 E C divided by L cube, this term 96 ECL cube, let we take this as K. So I will write, let this take is written as K. So you can write this equation that sigma is equal to K into Y, and this K will be equal to 96 for steel. This E is equal to 30 into 10 raised to power 6. You can check the property table. C is distance from neutral axis till top or bottom. So 1 over this distance will be equal to 1 by 8, and 1 by 8 is actually 0.125. So 1 divided by 8. Okay, so 1 divided by 4, if you take 1 divided by 4 half, this is 0.125. Okay, so you can also write it, C is 0.125 divided by L cube. So L length of this beam is 32 inch, so 32 cube. So when you calculate this, K is 10.99 into 10 raised to power 3 psi per inch, and you can also write this K is 10.99 kpsi per inch. Okay, moving further, we can also write that the minimum and maximum stress of Y and sigma can be defined by Y minimum and Y maximum. So we will understand this and then we will move forward. So looking at this figure, you can see the came and follower over here. So here preload is equal to 0, here preload is 2 inch, and here preload is 5 inch. So when in this condition, if this this roller this came moves and follower goes downward, so it will initial minimum deflection is 0, clear, Y minimum will be 0, and here when it's go downward, it's move like this, so this follower will move maximum 2 inch downward. We can say that due to the follower motion, this due to this came motion, the follower will move downward, and here you can see you have a preload of 2 inch. So you can see that this follower has been preloaded, and it is now moved with this, from this till this, it has moved due to the preload in this leaf spring. And further, if it rotates, clear, this follower moves further 2 inch, clear. Same is the case that in this case now it is loaded, preloaded to 5 inch, and further this, due to the rotation of this came, this follower will move downward. So what we can write is that Y minimum, let Y minimum is delta, and Y maximum is equal to 2 plus delta, where 2 is the 2 is the motion of this follower, clear, and delta is the preload. So from here you can say that sigma minimum is equal to K into Y minimum, which is equal to K into delta, and this sigma max is equal to K into Y max, or you can also write it as k into 2 plus delta. Okay. So these are the minimum and maximum stresses. So from this minimum and maximum stress, we can calculate sigma mean and alternating stress. Clear? As we know that sigma mean is equal to sigma max plus sigma minimum divide by 2. So sigma max is k into 2 plus delta plus k into sigma minimum is k delta divide by 2, and this will be equal to 2k plus k delta plus k delta divide by 2. So from here you will get sigma mean is equal to 2k plus 2k delta divided by 2. So if you take 2 k common from that, so we will get 1 plus delta divided by 2, and that will give you k into 1 plus delta. So sigma mean is equal to k into 1 plus delta. This is the value of mean stress. Okay, what will be the alternating stress? So alternating stress can be written as sigma max minus sigma minimum divided by 2. So sigma max is k into 2 plus delta minus sigma mean is k delta divided by 2. So k 2k minus k delta, sorry, plus k delta minus k delta divided by 2 will give you sigma alternating, and that will be equal to, this is sigma alternating, so sigma alternating is equal to 2k divided by 2. It means that it is equal to k. Sigma alternating is equal to k, and the value of k is 10.99 kpsi per inch. Oh, sorry, kpsi. I think I have made a mistake somewhere. So you can see this is, so this is kpsi only. Okay, this is the value of k. Now you have sigma m and sigma k. So what we will do, I will write sigma m over here. Sigma m is equal to k into 1 plus delta, and if you put the value of k, so 10.99 multiplied by 1 plus delta, and sigma a is equal to 10.99. Okay, so for what we will do is that in our first part we have to fill up this preloading. For preloading of 0 inch, 2 inch and 5 inch, you have to find sigma a and sigma m in kpsi. So for preloading, delta is equal to 0. So if you can see that delta a is 10.9, there is no other factor, so it means that sigma a is equal to 10.99 kpsi. So we will round it off, it will be equal to 11 kpsi. Similarly, for delta is equal to 2 inch, preload is equal to 2 inch, again sigma a is equal to 11 kpsi, and for delta is equal to 5 inch, again we have alternating stress is 11 kpsi. Okay, now what we will do is that if I draw a vertical line to separate it from that, so for delta is equal to 0, sigma m is, you can just plug it in this formula. Sigma m is equal to 10.99 into 1 plus delta is 0, so it is again, it will become 11 kpsi. So for preload of 2 inch, so put the value of delta 2 inch over here, so sigma m will be equal to 10.99 into 1 plus 2, and that is equal to approximately equal to 33 kpsi. So for preload of 5 inch, we have sigma m is equal to 10.99, or you can also write 11 into 1 plus 5, which is 65.9 kpsi. So these are the answers of our part first. So we will write this in this table. So this will be 11 inch, this will be also 11. For a preload of 2 inch, sigma alternating is 11, while sigma mean is 33 kpsi. For preload of 5 inch, sigma alternating is 11 and sigma mean is 65.9 kpsi. Now we'll move towards second and third part. So let's move further. Now we have been given that SY, SE and SUT values are given. I will show you. SY is 127, SE is 28 kpsi and SUT is 150 kpsi. So I will write it 127 kpsi, SE will be equal to 28 kpsi and SUT is 150 kpsi. So what we will do is that we will draw this graphs, that is for Gerber-Langer and modified Goodman failure curves. For that I will draw a vertical line to show this. On vertical axis we will take sigma a, and on horizontal axis we will take sigma mean. Okay, sigma mean. Okay, let one division is 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150 there. Okay, and similarly on x-axis 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190. So these are the value I have taken. Okay, so for Langer line we will need this yield strength. So yield strength is 127, so 100, 110, 127 is there. So this is yield strength. And on other hand we will take for Gerber, okay, for Langer, first we will draw for curve for Langer line. So for Langer line we will need yield strength on y-axis as well as on x-axis. So 127 will be somewhere here. This is 127 and this is SY is 127, and the unit of this alternating strength will be kpsi, and same is for mean, it will be also in kpsi. And if you join these two lines by using a straight line, so this line will be Langer line. Now for the second Gerber line, so for Gerber line we will need SE and ultimate strength. SE and ultimate strength. So SE is 28, so 28 will be somewhere here. This is SE 28 kpsi and ultimate is 150. So this point. So if you how we will join these two lines? So the Gerber equation will give you a curve like that. It should be like that. Okay, so we have drawn this orange color is Gerber line. I will write it. And the last one is modified Goodman diagram. So for modified Goodman diagram, we will need SE and SUT. So SUT is this one. But I will choose a black color. But for this modified Goodman line, it will be a straight line. So if you join them, it will be a straight line. So this black color, this I will do that. This is modified Goodman line. Modified Goodman line. Okay, now what we will do is that I will write it over here that a plot of Gerber-Langer and modified Goodman criteria. These are their lines. Our criteria is shown in figure or in this graph. So what we will do is that the three preload. Now we can see you have pair sigma 11 for 11 and 11 for preload of 0. For 2-inch preload, 11 is sigma A and 33 is sigma M, and for a preload of 5-inch alternating is 11 and 65. So what we will do is that we will plot these 3 points. So I will write it point A, which is 11 for preload is equal to 0. A dash will be equal to 1133 for preload is equal to 2-inch, and A double dash is 11 comma 65. Let me check it. The third, where is this? Okay, this is 65.9 inch, where the first value is sigma A and the second value is sigma M. So this is for preload of 5-inch. So we'll plot first point 11. So definitely this is 10 and this is also 10. So your first point will be this one. This point is A. Clear? Now second point is 1133. So 11, what we will do is that now for point A dash, you can see 11, which is sigma A. So sigma A will remain same and sigma mean is 33. So this is 30, this will be 33. So from here you can see at this point A dash you have sigma alternating is 11 while sigma mean is 33. So for point A double dash you have 65 is sigma mean. So this is 60 or this will be 65, and if you go above, so this point will be, at this point sigma alternating will be, you can see this sigma alternating will be 11. I will modify this point. These points are little bit here and here. So if you join all these points, so you can see you will get a straight line. You will get a straight line, and this line is known as load line. It shows the load. This line is load line. Okay. Since sigma A is constant at 11 kpsi, so the load line is horizontal and does not contain origin. That's why we have taken this as a straight horizontal line. Now we can see that here this load line is intersecting this linear line at this point and this um, Gerber line at this point. Clear? So what we will do is that we will find the sigma m value over this. Clear? And how we'll find this? uh, I will write that the intersection between Gerber line and load line is found, its value can be found from solving equation 6-42, and this equation is SA over SE plus SM over SUT whole square is equal to 1. And this point over which it intersect, at this point the stress will be Gerber line, at this point the stress will be SM. Clear? So how you will find that? This is the equation. I will show you this in the book 6-42. So we will move towards 6-42. It's on page number, I think, 337. Okay, so 6-42. Okay, so this is the equation. You can see you have SA, you have SE, you have SUT. So you can find this SM. How you will find that? So let's move. So from here you can see that SA over SE 1 minus is equal to SM over SUT whole square, and from here SM over SUT will be equal to square root 1 minus SA over SE, and from here SM will be equal to SUT into 1 minus SA over SE. Now you have the value. SM is equal to SUT is equal to 150, SE is 28. So I can write 150 into 1 minus SA is 11, which is sigma A alternating, sigma A divided by SE. SE is 28. So 28. So when you find this is mid-range strength. So mid-range strength comes out to be 116.9 kpsi. This is for Gerber line. Okay, now we will find for this Langer line, this SM value for this Langer line. So how we'll find the intersection of Langer line and load line is found from solving equation 6-44. So let's check that what is 6-44. So you can see 6-44 is this equation, the Langer first cycle yielding criteria. So SA plus SM is equal to SY. So I will write SA is equal to SM. SA plus SM is equal to SY. So from here SM will be equal to SY minus SA. So SY value is given 127 and SA is alternating, which is 11. So you can calculate, it will be 116 kpsi. So what we have obtained from that, that for this Langer line, this value is intersecting, this is 116, and for this Gerber line, this is 116.9. So both seems to be very close to each other. Okay, so we can write that the threat from fatigue and first cycle yielding are approximately equal in Gerber and Langer. Okay, now for modified Goodman, you can see that this is modified Goodman line and it's intersect with this load line at this point. So this intersection and SM can be obtained by using, I will write the intersection of modified Goodman line and load line is found from solving equation 6-41. So what is 6-41? Let me show you. This is for modified Goodman. This equation SA by SE plus SM over SUT is equal to 1. So I will write this SA over SE plus SM over SUT, since we are is equal to 1. So from here we will get SM over SUT is equal to 1 minus SA over SE. So SM is equal to SUT into 1 minus SA over SE. So SUT is 150. 150 minus SA is 11 and SE is 28. So we can get SM is equal to 91.07 kpsi. So this is for modified Goodman line. Now we have SM for all these three. It means that this point is 91. Sorry, if I have drawn it correctly, 91.07 kpsi. Okay, now what we will do is that we will move for the factor of safety, and for again for preload of 2-inch, we will find the factor of safety for first for this Gerber line, for Gerber criteria, and this Gerber criteria, this factor of safety will be equal to SM over sigma mean. What does it mean that for Gerber? Let me show you over here that this is Gerber line, SM is this value for Gerber 116.9, and your preload is this value for preload of 33. So it means that this is this much safer. So 116.9 divided by 33 will give you factor of safety. So I can write it over here that SM is 116.9 divided by 33 kpsi, that will be equal to 3.54 factor of safety. So for Gerber it is 3.54 factor of safety. Similarly, for Langer criteria, its factor of safety is yield factor of safety, and that is equal to, again for Langer this point is 116, and for preload of 33 at 33, so this will be 116 by 33. I can write it as 116 16 by 33, and that is equal to 3.54 as well. 3.52, sorry, 3.52. Now for modified Goodman, this same factor of safety is equal to SM over sigma mean. So SM for that is 91.07 divided by 33 will give you 2.75. So this is the answer of our first part. So we will fill that table. So for 2-inch Gerber is 3.54, Lagrange yield is 3.54, and this is 2.75. Now for 5-inch, I will do for 5-inch for preload. Delta is equal to 5-inch. So Gerber factor of safety NF is equal to sigma SM over sigma mean. So for preload, SM is 116.9 divided by, for a preload of that it was this A double dash, which is 65 point, where is the value, 65.9. Okay, so I can write it 65.9. Okay, so when you calculate it, it will be 1.77. Langer yield factor of safety will be NY, and that is SM over sigma mean. So that was 116 divided by 65.9, and that is equal to 1.76. And modified Goodman factor of safety will be equal to SM over sigma mean. So SM1 is 91.07 and sigma mean is 65.9, and that is equal to 1.38. So let me write this in this table. So this is 1.77, this is 1.76, and this is 1.38. And this was all about this problem of leaf spring that is under preloads. I hope you have enjoyed this video. Thank you.